Here's a sign in here.
Because I'm gonna forget it. I can, but I don't really want to.
So exam corrections to before you leave lab tomorrow. So what I want to do is go over the big picture and actually give you an orientation to the lab tomorrow, so you know what to expect when you come in. It also kind of breaks it up because otherwise the introduction actually takes more time than the experiment does. So I want to exhaust you on Tuesday. Oh, that's kind of good. Craig, it says your iPhone. Craig's iPhone. Glad to have you join us. Craig's iPhone. Okay, so big picture. We can relate any two quantities using this idea of the number of particles. As long as we have the recipe, that is the balanced equation. The trick then becomes, what are the conversion factors we get into moles with, and what are the conversion factors we use to get out of moles with? So it's all about the number of particles. The catch is we have no direct way of measuring the number of particles. We have to use relationships to tell us how many particles are present. So our classic one is mass, because that's the easiest, honestly. We just go to the periodic table. 1 mole equals the number of grams on the periodic table. So if carbon's 12 grams per mole and we've got 24 grams, we must have 2 moles of that carbon. If we're dealing with solutions, it gets a little trickier. We have to use the concept of molarity. Molarity equals moles per liter. And then finally, for dealing with gases, it's the most challenging. That's because for a gas, we've got the most things to keep track of. So we have this relationship that we refer to as the ideal gas law, meaning that the math works out for most gases that aren't sticky. This actually doesn't work well for water because water's got hydrogen bonding. We can solve it for the number of moles. N equals PV over RT, where P stands for pressure, V stands for volume, R stands for a constant, T stands for temperature in kelvins. And you are not supposed to be able to do all this yet. This is still an overview introduction. The good news is those same 3 relationships are the ways we get out of moles too. So if we want to know how many grams, we look up the conversion factor on the periodic table. If we're dealing with a solution, we use a relationship called molarity. Molarity equals moles per liter. And if we're dealing with gases, it's the same relationship. We're using this ideal gas law, PV equals nRT, but typically we're solving for volume instead. Volume equals nRT. So the only difference between into moles and out of moles is kind of the way we set up the conversion, the way we set up the algebra. We're usually looking for a different quantity, but the relationship is the same one. Now I will go over this overview, this mole map, I call it. I'll go over this a couple more times over the next couple weeks. As we get to that point, you don't have to keep writing it down. I encourage you to write it down, but if you feel like you've got all the individual relationships straightened out, then you don't have to keep copying it down. But this is the same pattern over and over again. Anytime we're talking about chemical quantities, is it one substance? Okay, we're just talking about how to describe that one substance in different ways. Or is it more than one substance? This one substance reacts and either uses up or produces another substance. Then there's a balanced equation involved. And we've got to get into moles, between moles, and back out of moles for that particular substance. So in particular, tomorrow's lab, and I'll kind of describe it verbally, and then I'll show it to you, and then we'll get into the details. You'll be provided with a Ziploc bag. Your job is to inflate that Ziploc bag using carbon dioxide produced from mixing baking soda and vinegar. And you're to determine how much baking soda and how much vinegar go in the bag. So the bag will inflate a minimum amount as defined by being able to support a weight, a 1 kilogram weight, 5 centimeters off the lab bench, but not overinflate to the point of popping. So if it pops, it fails, and you have to start over again. And if it doesn't inflate enough, it fails and you have to start over. That's the challenge. What I want to do is show you how we can use the mole map as well as an additional kind of experiment within the experiment to fill that bag. So let me show you the chemistry first. And so I'll switch over. I'll zoom in as I need to. All right, so this is baking soda, white powder. And in goes some vinegar. It's a fresh bottle there. Set other bottle in the bracelet there. I go Walmart vinegar. That fizzing is carbon dioxide. There are some other products that are produced, among them water and a compound called sodium acetate. We'll write those equations out in a second. But essentially that jar is being filled with carbon dioxide. The reason why I put the foil on top is to help kind of trap the carbon dioxide. That was a nice frame. That's cool. All right, the reason why I put the foil on top was to trap the carbon dioxide. So I could show you one of its properties. Nevada, if you catch the lights for us. Oh my goodness, was that? I hope that wasn't on my screen, but I hope it wasn't on theirs. I can see the flame jumping off the candle. Can you guys see the flame jumping off the candle? Oh, yeah. So the candle is going out at the point where the carbon dioxide concentration really builds up, and it's filling from the bottom up because it's a really dense gas. We'll talk about gas densities in a couple more days. I like just trying to see how far I can get the flame off of the candle. And the fact I get really good smokes off of the wick, so I can relight the candle at several inches distant. The reason why I can light that, we would call it smoke, but it's not actually smoke, it's actually condensed wax. It's flammable. It's the same reason why you're not supposed to smoke at gas stations, because of the fumes from the gas evaporating into the gas state can be ignited at several feet away. But this gas is filling up a container that's about 2,500 milliliters. So the question is, would that be enough to fill up the bag that you're looking at? Mind if you catch lights for us, please? So in lab tomorrow, you'll get a Ziploc bag. And the first thing is you have to figure out how could you get it to be filled in such a way that you could pretend like it's filled with the gas. I'm going to pretend by filling it with just some of my exhalation. And I'm just going to use a stapler as my weight. And I could grab a ruler and measure that distance. Is that stapler 5 centimeters off the lab bench? And the answer is yes, it's more than 5 centimeters. So this volume would be enough. So my question to you guys is, what is the volume of this bag right now? What would you guess?
That's probably what, a quart Ziploc sandwich
It
bag?
is a sandwich bag, yep.
I don't know what that is though.
Technically it's a quart, but we want to try to get a little bit more accurate measurement. A little bit more area. So we could use length, width, and height, right? Grab a ruler here. So we got 12 centimeters wide, 12 centimeters across, and then 5 centimeters high. I'll work on the whiteboard a little bit. Got a marker, I'll try to do it up here. Oh my gosh, we're all out of whiteboard markers. I'll switch back over here. So one approach, we can use geometry. 12 centimeters by 12 centimeters by 5 centimeters. Length times width times height. 720 cubic centimeters. Which is equal to 720 milliliters, which is the same as 0.72 liters. Now, just out of curiosity, Nevada identified it as a quart-sized bag.
46.
946. So we're actually doing okay. Versus 1 quart. Thank you very much. 946 milliliters or 0.946. And so the reason for that difference is twofold. The first is I didn't fill the bag as much as I could have filled it. And so as long as you have filled it at least enough to hold a weight 5 centimeters off the counter, and as long as it doesn't pop, you're in a zone we're considering a sufficient inflation of the bag. But geometry is not the only approach we could use. What's another approach we could use to figure out the volume of that bag? Displacement. We could use displacement. So I got a beaker here, fill it up with some water. Okay. Put a little bit more water in there. Try to get right to 1,500. As close as I can, I guess. That's too high. That was zero. All right. So it is 700-ish milliliters. If I put this into the beaker, what should the beaker read? About 2,200. So here's 2,000. Whoops. Move it up just a little bit. So there's 2,000. Here's 2,500. This would be 2,250 right here. So I'll put the bag in. It takes a little bit of doing because, of course, it wants to be out of the water. That's not too bad. So I could use displacement. Or the flip side is I could fill the bag. This takes a little doing, and this is where your lab partners really come in handy. And so you make sure that the bag is filled with water instead. Verify that it's at least 5 centimeters off the lab bench. Fill the bag with water. Make sure it's at least 5 centimeters off the bench. And then you can empty the water into a container and measure its volume. Now we've been saying what, it's about 700, somewhere between 700 and 900 milliliters. About 750. The point is, there are multiple ways to get at a volume, any measurement, but volume in this case in particular, and you can use any of them as long as you document what you do to get to the volume, get that measured. But here's why that volume measurement is important. Because that volume is going to be entirely made of carbon dioxide. We're going to use that volume of carbon dioxide to figure out how many moles of carbon dioxide must be present, how many particles of carbon dioxide must be present. And then I'm going to give you the balanced equation that ties it to how much vinegar had to be added. And then we'll use the molarity of the vinegar to figure out what volume of vinegar we need to use. We're going to do that same set of calculations again. We're going to start with the volume of the bag filled with carbon dioxide, figure out how many moles of carbon dioxide are involved. So that's the same. But then we're going to turn the balanced equation and say how much baking soda needs to go in the bag. The nice part about the baking soda is it's a pure solid, so we can just weigh it out. We'll be able to go to the periodic table and figure out how many grams of baking soda are involved. As opposed to the vinegar, that's where our experiment within an experiment comes in. We've got to figure out what the concentration of the vinegar is. In other words, what we're told on the label is that it's 5% vinegar by volume. We're not being told how many particles of vinegar are present. And that's what we really need. So we'll have to do a little experiment with an experiment to figure out what the molarity is so we can relate the number of particles to the volume for the vinegar. So we're using the mole map to get from the carbon dioxide to the baking soda, from the carbon dioxide to the vinegar. Questions about the big picture before we dig into the weeds? All right. We're saying the bag is 0.72 liters. What I'm telling you is there's a relationship for dealing with gases that goes like this. The pressure times the volume equals the number of moles times a constant times temperature. Now, at this point, I should emphasize again, you are not supposed to be an expert at this relationship by the time we're done today. This again is still part of kind of the overview, kind of introducing you to the big picture. So we know what the volume is. And I'm telling you here in Sheridan on this particular day and most days, once we get extreme weather, one way or the other, the pressure is 0.88 atmospheres. I'm telling you the temperature in the lab is about 22 degrees Celsius. If we add 273, we would call that 295 kelvins, and that's the value we'll want to use. And I'm telling you the value of R that ties this whole thing together is recognized by scientists as being equal to 0.0821 liters times atmospheres over moles times kelvins. You don't have to memorize that number. That'll be provided for you on the exam. Now, myself personally, I like to get the algebra out of the way first. So I know the pressure, I know the volume, I know the constant, I know the temperature. The only thing I don't know is the number of moles. So I'm going to solve for the number of moles. I'm going to divide through by RT on the right, which means I divide through by RT on the left. The number of moles is equal to the pressure times the volume divided by that constant times the temperature. Let me pause there. Questions? So the pressure, 0.88 atmospheres. The volume of the bag, 0.72 liters. The gas constant, 0.821 liters times atmospheres over moles times kelvins. And temperature, I'm telling you in the lab, is about 295 kelvins. I'm going to emphasize this number because that's really the only experimental value. Each group is going to get their own Ziploc bag. Bag may be one of several sizes. That's the one you directly measure. The other experimental values, the pressure and the temperature, those are pretty much fixed because of where we are altitude-wise and where the college decides to set the room temperature. I actually don't have any control over that. They've got the little remote sensor things, and in a pinch, I could call them up and say, hey, it's getting hot or cold over here, and they'd send somebody over to make the adjustment, but really not much I can do but open up the door. Bless you. Taking a look at units, atmospheres cancel with atmospheres, liters cancel with liters, kelvins cancel with kelvins. The only unit that does not cancel is moles, which is good because I'm looking for how many moles of carbon dioxide does it take to fill the bag. Now, there are two different ways we can approach this. Just wanted to make sure in terms of calculator usage, we're doing this the right way. So one approach is to do 0.88 times 0.72 divided by 0.0821 and divide by 295. You have to do both divisions because both those numbers are on the bottom. The other approach is to do 0.88 times 0.72 divided by and use parentheses. If I use parentheses, then the calculator understands you're dividing by both numbers, 0.0821 and 295. You got to use parentheses though, if you're going to do that. So you either divide by both numbers or you divide by the whole parentheses. Now, the fact that I'm going over this bit of calculator operation is my way of communicating to you that for whatever reason, people have trouble with this. So I'm trying to help you avoid a little road bump here. If you're dividing by two quantities, you've got to divide by both quantities. Doesn't matter, I get the same number, 0.026. That's how many moles of carbon dioxide are involved. Your number of moles will vary based on the size of your bag. The bigger the bag, the more particles of carbon dioxide you need to fill the bag. Now, that carbon dioxide is being produced because the acetic acid is reacting with the sodium bicarbonate. And the most obvious and dramatic product is that carbon dioxide. It's being produced as a gas. We're also getting a little bit of water, and we're getting the leftover pieces, sodium ions, and what we call the acetate ion. Sodium acetate. Now, this is the historic name for acetic acid. Systematically, we've been calling it ethanoic acid. And ethanoic acid is recognized. Acetic acid is used just as a historical after effect. But that's where the name acetate comes from. It's another polyatomic ion. It's not one of the ones I added to your packet back in Unit 2. I'm sharing it with you here. If we count up the number of carbons, there are 1, 2, 3 carbons on the left-hand side. There are 1, 2, 3 carbons on the right-hand side. If I count up the number of hydrogens, there are 3 plus 1 makes 4, plus another one makes 5. There are 5 hydrogens on the left-hand side. 2 plus 3 make 5 on the right-hand side. There are 2 oxygens plus another 3 make 5. 5 oxygens on the left-hand side. 2 plus 1 plus 2 on the right-hand side. This equation is balanced. And what's important is that for every 1 acetic acid, you need 1 baking soda to make 1 carbon dioxide. Now, the good news is it's all 1 to 1. So what that means is my 0.026 moles of carbon dioxide will require 1 mole of baking soda for every 1 mole of carbon dioxide to be made. And my 0.026 moles of carbon dioxide will require 1 mole of the acetic acid for every 1 mole of carbon dioxide that I want to make. Now, sure, you might ask, why in the world do we bother with multiplying by 1 and dividing by 1 when you get the same number? And the answer is because not every chemical equation is 1 to 1. So we always have to have it in there in the event that it's not a 1 to 1 relationship. But yes, mathematically, what it means is we need the same number of moles of baking soda and the same number of moles of the acetic acid to fill this bag. Now, again, remember, these numbers will be different if you've got a different bag, because if you've got a different bag, you'll need a different amount of carbon dioxide. Therefore, you'll need a different amount of baking soda and a different amount of vinegar. Question so far? Okay, so I'm going to clear the board. I'm just going to borrow these 2 numbers here. Copy here. 0.026 moles of baking soda 0.026 moles of acetic acid. So the baking soda is the easy one. It's a pure solid. I go to the periodic table, 84 grams of baking soda for every 1 mole of baking soda. .026 times 84, 2.18 grams. Now, just a quick check. Where have you seen this number 84 previously? Where? In lab 2 weeks ago. So it's the same number that we used to figure out how many moles of baking soda were in the cup. 84 grams per mole. It doesn't change. It's consistent for that substance for all eternity. 84 grams per mole. What this number is saying is, if you had this size bag and you wanted to fill it to that volume, you would need to put 2.18 grams of baking soda into the bag. That's all. That's what the number is saying. Unfortunately, the vinegar is not so easy. The vinegar is a solution. Most of what you're pouring out when you pour out vinegar is water. But we don't know the relationship of how many particles there are of vinegar per volume of vinegar, because the bottle is not labeled based on moles per liter. The bottle is labeled based on volumes. 5% of the volume was pure acetic acid added to the solution. We don't know how many particles that represents. What we'd like to do is be able to use the idea of molarity. We know the number of moles. If we only knew the molarity, we could then solve for the volume. Because it's a solution. We want to be able to pour it out. That's the easiest way to measure out a solution. But we can't do that without knowing the molarity. So here's the experiment within the experiment. What's the molarity of the vinegar? What is the concentration of the vinegar? In order to figure out the concentration of the vinegar, we're going to take advantage of a second reaction. That acetic acid has one hydrogen that comes off readily. And in the presence of a substance called sodium hydroxide, that hydroxide has a negative charge, and it will pull the hydrogen off of the acetic acid. The result is water. Plus sodium acetate. Sodium has a plus charge, acetate has a negative charge. Fortunately for us, it's a 1-to-1 relationship. Every 1 vinegar will use up 1 sodium hydroxide. So we're going to use the sodium hydroxide to figure out what's going on with the vinegar. The way we do that is a process called a titration. Let me show you what a titration looks like. Most common approach for doing a titration involves this device called a burette. Burette has got a valve at the bottom. If the valve is perpendicular to the tube, it's closed off. If the valve is parallel with the tube, it's open. What I do is I add a substance to the burette. In this case, I'm adding sodium hydroxide. Doesn't matter how much you actually put in the burette. I like to put in just enough to flush out the tip of the burette. There's a picture in your lab manual going over how to read the burette. That's actually, I need to take out a little bit more. But you have to be careful to read the bottom of the meniscus. .70. I'll record that over here. My initial volume in milliliters, 0.70. I'm gonna add sodium hydroxide and record a final volume. And then I'm gonna record the total in milliliters. Data table go on there. I'm gonna measure out a sample of vinegar. The volume of your sample doesn't matter, just so long as you know what it is. Mine is going to be 25 milliliters. Just a little bit more here. .25 milliliters of vinegar. As a practical matter, we want to be able to mix the two together. So I'll provide everybody with stir bars and stir plates. You'll have electrically powered ones. This one's a portable battery powered unit. What the stir bar stir plate combination does is stir the solution for me. Add sodium hydroxide. But there's one last key ingredient. As sodium hydroxide is added and uses up the vinegar, I'll need some indication that all the vinegar is gone. And so I'll have you add drops of this phenolphthalein. This is a substance that turns color in the presence of excess sodium hydroxide. And it's stuck in there. There we go. You only need 1 or 2 drops. So we're adding the sodium hydroxide. It's going to use up the vinegar. And then in a couple of seconds, I'll show you what the concentration of sodium hydroxide is. So we can work out the concentration of the vinegar. Open up the valve. And at first, nothing discernible happens because there's so much extra vinegar. Let me zoom in here. What I'm doing is I'm looking right where the sodium hydroxide hits the solution, because if anything's going to change, it's going to be right in that location. That pink color is the phenolphthalein. Its chemical structure is changing because there's an excess of sodium hydroxide to react with. As long as there's vinegar around, there's no hydroxide to react with the phenolphthalein. But as soon as I add that extra couple drops and there's no more acetic acid present, then the hydroxide turns on the phenolphthalein and causes it to change shape and changes color. Now you want to let it sit for a little bit just to make sure the pink color stays put, that there isn't some sort of mixing that still needs to happen to get to some of the vinegar that might be present. But once it stays pink, you can check the final volume. Final volume here is 26.60. Back to our little mini data table here. .60, and so that means our difference 26.6 minus 0.7. We added 25.9 milliliters. Oops, sorry, I've got the unit already. 25.9 is our total. So I'm going to try to. Oh, I didn't want to zoom out that much. No. I tell you, between the water in the beaker, the vinegar in the graduate cylinder, now the zooming, I just can't quite get it just right. Oh, actually, though, that's ironic as I think about it, because for the first time in forever, don't worry, I'll make it up to you, I promise. For the first time in forever, like our candy in versus candy out, like perfectly balanced last night. So normally we send our kids out to go get candy. They come back and we let them keep some good stuff, but mostly we just recycle it so we can give it to the people that are coming to our door. And normally it ends up balancing out. So we have extra candy. And this is the first year that like it perfectly balanced out. I have no extra candy for you. I will bring extra candy for you shortly. I apologize for not having it on hand. Anyway, so let's see if I can just zoom here and move the whole thing. It's creating a little space for myself. There we go. All right. So we're going to use the idea of molarity, moles per liter. What I know from the titration is this. I made the sodium hydroxide to have a certain concentration, just like you guys made the copper sulfate solutions last week to have a certain concentration. I write it on the bottle to remind myself. .8132 molar sodium hydroxide. I know the sodium hydroxide is 0.8132 moles per liter. I know in this titration, it took me 0.0259 liters to do the job. I'm trying to figure out how many moles of sodium hydroxide I added. X. So my number of moles is equal to my molarity times the number of liters of the solution that I used. .8132 times 0.0259. I must have used 0.0211 moles of sodium hydroxide. The balanced equation is telling me for every one sodium hydroxide I added, there must have been one vinegar in the solution. Let's scoot this up just a little bit. If I have 0.0211 moles of sodium hydroxide, every one vinegar must have used up one sodium hydroxide. So there must be 0.0211 moles of vinegar. Molarity is moles per liter. I know there are 0.0211 moles of vinegar in every 0.025 liters of vinegar. Now, let me just check, see if you were paying attention. Where did I get this 0.025 from? That come from?
It's the amount of vinegar that
It's the volume of the vinegar. Now that's up to you. You guys can do any volume of vinegar that you want to test. The bigger the volume of vinegar, the longer the titration is going to take. The smaller the volume of vinegar, the shorter it's going to take. But you want to use at least 10 milliliters. Anything less than 10 milliliters, and now you've got to be really good at your titration technique to get a decent result. If I take, sorry, let me write that down. Sample of vinegar volume. So that's the sample of vinegar. If I take 0.0211 divided by 0.025, I get a molarity of 0.844 moles per liter. That's the molarity of the vinegar. That's what I need up here. 0.844 moles per liter equals 0.026 moles divided by some volume. In other words, I'm trying to figure out how much vinegar to pour in the bag so I have enough dissolved vinegar molecules to do the amount of reaction I need. X is going to be equal to 0.026 moles divided by 0.844 moles per liter. So essentially, if I want to get X by itself, I have to get out of the fraction. So I can multiply it onto this side and then divide by the 0.844 on both sides. Just using the numbers here, 0.844 equals 0.026 over X. I need to multiply by X. I've got divide by 0.844. X is equal to 0.26 divided by 0.844. Zero two six divided by 0.844 equals 0.031. That's liters, because my moles cancel. 0.031 or 31 milliliters. To fill that Ziploc bag, I need to put in 2.18 grams of baking soda and 31 milliliters of vinegar. Now, the final challenge that you'll have to face on Tuesday is how do you get both things in the bag without them touching? Because you can't have them touch and make carbon dioxide that could escape the bag. Otherwise, you won't have the right number of particles. So you got to get them both in the bag without them touching. Questions? So experimentally, there are really only two numbers that you need to measure directly. The first number is what is the volume of the bag? Second number is what is the volume of sodium hydroxide it takes to use up the vinegar that you're given. Questions? All right, so when you come in on Tuesday, I'll hand you your Ziploc bag and turn you loose. If you have questions, you just call me over and we go through the calculations again for your particular bag. And I'll help you through it. But the goal is to have you inflate your airbag so it holds a weight at least 5 centimeters off the surface of the lab bench without popping. There is a supplemental reading that's available through under the assignment for this investigation. It has to do with the history of actual airbags. This chemical reaction is way too slow to make for real deployment in an actual airbag. The substances that are used to actually fill the airbag are much too reactive for us to use in lab. If you're looking for a fun time, you can go track down like YouTube videos for airbag. It's like airbag deployment challenge or something. It's not, again, YouTube challenge, don't do it. But if you sit on the steering wheel and deploy the airbag, it's enough force to launch an individual into the air about 10 to 15 feet. It's really a dramatic reaction. Anyway, so there's a reading assignment associated with it. We'll be able to go through that during our time on Tuesday as well. All right, folks, thank you all very much. I'll see you all tomorrow. I'm cracking.